Hi.
So, this year we're celebrating 10 years of continuous delivery, right? I must say I very much respect the work that you're doing. Welcome again at Code Camp. It's been like 1.5 months since you've been at the Architecture Day at Code Camp. So Dave, how does it feel to have such an influence on the industry, and how do you feel the responsibility of an entire set or thousands and probably companies following your advice and actually transforming their business based on the experience that you're sharing?
Well. It's a very pleasant. The success of the book, and more importantly, the success of the ideas, has been a very pleasant surprise. I don't think that Jez nor I anticipated the degree to which the book would be a success, and I think that now I feel more strongly than when the book was published that continuous delivery is an important thing. I think it qualifies as being widely recognized as the state of the art in software development practice, and that's an amazing thing to feel. I don't feel too much weight of responsibility because the ideas aren't all mine. So it's not just me providing those ideas. We pulled together a whole bunch of ideas in this book, and we built upon the shoulders of giants, I think very strongly in the shape of Kent Beck. I think continuous delivery is an extrapolation of extreme programming. I think continuous delivery takes it just a few steps further on, but similar kind of ideas. So I think that this is part of an interesting journey that our discipline is undergoing. We're growing up. We're finding things that really work. I think that one of the reasons why continuous delivery as an approach is important is really related to my talk today, which is that I think that it's really about software engineering. I think it's about genuine engineering practice, and so that gives us an opportunity to magnify our talents. I'm sorry, go ahead.
Who's stolen the engineering? Who has stolen the engineering? So we want to get it back.
I think a variety of people have stolen the engineering. I think that we've misappropriated what engineering means, and I'm going to talk about that a little bit in terms of what I think engineering is not and the way that we've thought about it. In most disciplines, what engineering means is, to put it really simply, it's the stuff that works. I think in our discipline, almost uniquely, there's certainly a group of people that, people like the craftsmanship movement and agile practitioners like me, who have come to think of what we tend to think of as software engineering as the stuff that doesn't work. That's wrong. That's backwards. So how do we take it back and kind of position real deep engineering thinking, which I think is important, but in a way that is agile, allows you to practice, is backed up by techniques like continuous delivery and so on. So that's really my theme for today.
Excellent. So before going straight to the point, I was having a curiosity. So did you actually have the time, took the chance to celebrate the 10 years?
Not very much. So my wife and I had a glass of wine together on the day. We did. Jez and I did for the first time. I think for the first time ever shared a stage at a conference early in January before the global pandemic began in Seattle, and we got to talk about 10 years of continuous delivery together, which was a great amount of fun. I haven't seen Jez for a little while, so it was very nice to catch up with him and for us to share the stage and talk about these topics together.
Excellent.
As usual, I talked a bit too much.
No worries. So thank you once again for being with us. Congrats for the great work that you're doing. And now, please feel free to share the presentation, and you have the floor.
Thank you very much. So let me just share my screen. There we are. I hope everybody can see my screen now. So let's begin. So what do I mean by taking back software engineering? I started my career with job titles like software engineer, junior software engineer, senior software engineer, whatever. And during that time, the stuff that I was doing bore no relationship to anything else that anybody would recognize as engineering. Later in my career, I began working for a bunch of organizations that really didn't like the term engineering. And so we started to call ourselves other things. We called ourselves software developers rather than engineers. I worked at one place where we had a couple of grand wizards, I seem to remember, and a meme wrangler. But these are, you know, we kind of shied away from the term engineer because we didn't think it was appropriate to us. And then in the latter part of my career as a hands-on software developer, I started working on some projects that took some genuine engineering thinking and engineering discipline to achieve. They were genuinely difficult projects, and I don't think would have been possible of being realized without the kind of thinking that engineering can bring to the table. And so I changed my mind about what engineering really meant in the context of software development. Meantime, during that period, I was writing the continuous delivery book. So you'll see the crossover as we go through my presentation. We'll see the relationship between the ideas I have. So let's start looking into this. Let's start thinking about what engineering is. I think for most people, at least for many people, certainly for me during some period in my career, if you'd mentioned the term software engineering to me, I would have thought of something like this. I would have assumed that what you were talking about was something that looked like this. This is a UML diagram, and whether this is to engineering, this is to software engineering what a soldering iron is to electrical engineering. It's a tool. It's nothing more than a tool. It certainly doesn't comprise an engineering discipline. It might be a good tool, it might be a bad tool, but it's only a tool. It's certainly not what we could think of as an engineering discipline for software. We often think about process as a tool too for software development, and this is the diagram that people use to represent the Scrum process. And this certainly had an impact on our industry, and in many ways a positive impact, but this too does not define engineering. Do you have any idea how many times the documentation for Scrum mentions the words code or software? And I'll tell you the answer's none. In the official documentation that describes Scrum, it doesn't mention those terms. So it certainly can't be considered an engineering discipline because it doesn't talk about the actual thing that we produce. That doesn't mean that I think that Scrum is bad or evil. It's just focused on project management. It's an effective project management technique, and it's as useful to plumbers as it is to software developers. So that doesn't really answer our question. Certainly in the organizations that I worked in, the idea of software craftsmanship, if you'll forgive the slightly sexist term, that kind of took off. And I think there are some good reasons for that, which I'll explain in a couple of slides. But craftsmanship is kind of by definition not the same thing as engineering. Craftsmanship is the way in which we've built things for tens of thousands of years. That's the way that all human creativity worked until we invented engineering 200 or 300 years ago. And so this really doesn't classify as an engineering discipline either. Again, it certainly has its positives, which we'll talk about, but it's not engineering. So let's think a little bit about what this means in different contexts. So we can think in terms of craft. As I said, most of human experience is based on the creation of physical things by hand for about 200,000 years, actually longer. If you look at the age of stone artifacts, this predates our species. Everything was the the product of craft-based production techniques. And the problem with craft-based production techniques is that they're so variable. It depends on the skill of the individual craftsman. It also depends upon the human levels of precision. You can't get, in a craft-based production process, you can't go beyond the accuracy of human precision. Imagine just for a moment a craft-built iPhone. That's a ridiculous concept. It doesn't make any sense. Even the prototype for something as complicated as an iPhone or any smartphone takes deep engineering. It takes all of the tooling and techniques and maths to be able to design even a prototype for such a thing. You can't hand build something like that with that degree of precision. Human beings are simply not that accurate. Later, as we started evolving our production of things, we got into mass production techniques, and we started thinking about building things more efficiently, and mass production became the norm for a large part of the 20th century. But it actually began before then. The first real impact of mass production was during the American Civil War. And there's kind of an amusing story. If you can have an amusing story about something as horrific and horrible as a war, this is probably one. The story of the man who wanted the contract to produce the rifles for the northern states in the American Civil War is interesting. He went to Congress one day with a sack full of rifle components, and he emptied the sack out onto the floor of Congress, and he asked the congressman to select individual pieces of the rifle from which he assembled a whole rifle. That was the first time in human history where that was possible. And that depended upon the standardization of components, the accuracy of the production of those components, the accuracy of measurement, and so on and so on. Prior to that, if you'd wanted a rifle, the whole thing would have been built from scratch by a single human being, and it would have been unique to that human being. If you wanted it repaired, you probably would have taken it back to the same person. When you bought your rifle, it came with a mold for the bullets, because the bullets were each slightly different sizes. One of the absolutely horrific things about the American Civil War was that it was the first mechanized war. It used mass production techniques to generate standardized armaments, and so you know, they waged war, I suppose, more efficiently in some kind of macabre kind of form. But mass production gives a big step forwards in terms of craft. It improves the repeatability and reliability of production processes. At the end of the Second World War, I'm starting to realise that my talk involves quite a lot of talking about wars so far. I get past that, don't worry. So at the end of the Second World War, a man called Edwards Deming went to Japan and helped reinvigorate their economy. Japan had some interesting prior cultural tendencies towards what we would now think of lean production techniques. Deming went and applied some more scientific rigor and helped boost that by coming up with applying plan, do, check, act and the scientific method to solving problems in production. He gave birth to what ended up being lean, what we would now think of as lean production techniques. Now, lean is interesting. Lean is often counterintuitive. It's a pull-based system rather than a push-based system. It looks at eliminating waste. And my kind of elevator pitch soundbite for lean is that you're trying to maximize the output of your process for the minimum amount of input. For the least amount of work, we want the most amount of output, is kind of one way of thinking about what you're trying to do with lean production techniques. Now, on this picture is one of the things that has kind of plagued our industry. So where are we as an industry? We are not a mass production industry, but that thinking has plagued our industry. If you think about our problem is interesting. So think for a moment, look around you, and I've got a coffee cup in front of me with some coffee in it, And imagine trying to create something like my coffee cup. The design of the coffee cup is certainly interesting, and kind of coming up with the shapes and the colors and all of that kind of stuff, where we're going to put the handle, all that kind of thing is an interesting problem. But the really difficult problem, if you want to manufacture these, is productionizing that process, changing the one-off craft-based act of generating a mug out of some clay or ceramics or whatever it is, and then amplifying that so that we can produce millions of these with a certain level of quality and at a certain level of price. The second part is a much more difficult thing. Mass production was designed to solve that problem. Interestingly, in software, we never have that problem. If you think about building a software system, however complex it may be, we can effectively create a copy, tens of copies, thousands of copies, millions of copies at the push of a button. Essentially, the cost of production for us is as close to free as doesn't matter. It's essentially zero cost. So ours is not a production constrained discipline. Our problem is always about the first part of the problem. It's a problem of design, which means that it's a problem of exploration and discovery and creativity. And that's really the focus of what we should be doing. So mass production is a really, really bad fit for software development. And yet most of the recent history of our industry is trying to force fit mass production techniques like waterfall development onto a non-production problem, which is software development. And we've seen the results of that. We've been trying to make waterfall work for at least the 40 years that I've been involved in software development, and it's never really worked. We've now got data that shows that it doesn't work as well as other things. So that's busted. That doesn't work. That's not where we should be shooting for. At the start of this century, as I alluded to before, we started to think that that doesn't work. What else should we be? And we kind of ditched mass production and that kind of thinking and started thinking about, well, what about if we start applying craft thinking? And that's a huge step forward. I think that's where we are right now. I think that's where we're at. Mostly, we recognise that this is to do with the craft of people, the creativity, the ingenuity, and that's all true. So that's a much closer fit to what we want. The problem with that, as I described before, is that that's limited. It's limited in its scope, and its scale, and its efficiency. So I think that where we should be aiming for really is here. We should be aiming to apply lean production techniques, working so that our processes and approach are so efficient that they're almost transparent, and therefore allowing us to amplify the creativity and so on that our craft and our skills bring to the table. So when we start thinking in those sorts of terms and applying these kinds of ideas to software development, the impact is enormous. The impact of engineering style thinking is quite dramatic. And we now have, for the first time in the history of our industry, some more definitive, more accurate measurements of software projects' performance in the form of the State of DevOps report and the wonderful Accelerate book, which describe these ideas, that show us the impact of applying this kind of thinking in software projects. Now, I've been talking about engineering and these sorts of ideas for quite a few years now in various contexts. And as a result, I kind of end up in an unusual quantity of discussions about bridges. And that's because what happens usually is that I start explaining my ideas about engineering, and at some point somebody steps forward and says, no, but this, we're not doing bridge building. And of course, we're not doing bridge building. But I think that there's two interesting parts to that problem. The first is that one of the really complicated problems of bridge building is kind of the logistics of getting all the materials and all that kind of stuff to the right place at the right time. And you can certainly apply lean techniques to that kind of stuff, but really, you know, that's a different kind of problem, and again, not really the kind of problem that's our problem. And the other thing is that when we start thinking about bridge building is not all the same either. So, you know, if you're designing the first ever bridge of a certain kind, that's going to be a very, very different experience to building a standardized kind of off-the-shelf bridge that you've built 50 times before. If you're doing the second class of things, that's a production engineering problem. That's a civil engineering problem, straightforward. If you're in the former case, if you're building, I don't know, a fiberglass bridge across the Black Sea, you know, that's going to be the first of its kind, and you're going to be doing finite element analysis and wind tunnel tests and lots of maths and building little models to try and figure out how it works and testing the strength of the models and all of those kinds of things. That's going to be much more an exercise in discovery, in design and discovery. So bridge building is not really what we think about it, and is often, you know, and certainly not representative of what we do. But that's true of any form of engineering. So engineering is not the same in all disciplines. It has some common features. There are some ideas that are consistent in engineering disciplines, but bridge building is not the same as electrical engineering, which is not the same as rocket engineering, which is not the same as chemical engineering or automotive engineering or any of these things. And so the first thing that we can be certain of if we start thinking about what engineering should mean to us is that it will be different to any other form of engineering. It will be ours, and it will be focused on our constraints and the nature of the problems that we solve. So the first thing that I'd like to say about software engineering is that it will be different to other forms of engineering, and it should be. It will be ours. The other thing that's kind of interesting when you start thinking about engineering is that it's different at different scales. Here are two structures. On the left-hand side is a small, simple structure. And on the right-hand side is the tallest building in the world. Both of these are engineered structures. You can bet if this was a shed that you bought from your local, somewhere like IKEA or something like that, then they would have engineered that down to make sure it's made of the fewest number of components and the lightest pieces of wood and all of that kind of thing. But it's absolutely obvious looking at these two pictures that the engineering that went into the building on the left is not at the same level or of the same scale as the engineering that went into the building on the right. If you're building something like the Burj Khalifa on the right in this picture, then you're going to again be building models and computer models and doing finite element analysis and all different kinds of techniques. But you're going to probably build a model and put it on a table that shakes with representative version of earthquakes that are in that part of the world, and all of those kinds of things in order to be able to learn about enough to be able to construct a building like that. So engineering is different at different scales. Now that's interesting for us because that's not quite so obvious looking at things in software as it is for things like buildings. Looking at these two, as we said, it's obvious that the engineering here is different. If I write some software for, I don't know, the Mars rover, and I write some software for my mom's cake shop, just looking at that software from the outside, it's not evident to the average person in the street that there's a difference between the engineering that goes into those two things. But there should be, there probably should be. So engineering is also different in different contexts and at different scales. Let's start digging into this in a bit more detail. Here's a definition from Wikipedia of engineering. Engineering is the application of mathematics, empirical evidence, scientific, economic, social and practical knowledge in order to invent, innovate, design, build, blah, 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 blah. a bunch of work. Whenever you look at descriptions of engineers, you get a bunch of common ideas. I think the founding idea here for me is this idea of of really applying scientific rationalism to solving practical problems. So here's my working definition. When I talk about engineering for the rest of today, what I'm really talking about is this. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. That's what we're trying to do. If you think about the history of engineering, engineering really properly started around the time of the Enlightenment and the introduction of the invention of science 300 or 400 years ago. And that's when we really started applying the ideas of science, the measurement and controlling variables and all of that, experiment and all those kinds of ideas, and applying those to solving practical problems. And we can see the impact on our world of that kind of thinking. I would argue that that science in general, but engineering specifically, is really the difference between our modern high-tech civilization and the agrarian civilizations that existed for hundreds of thousands of years before it. So what are the fundamentals of an engineering approach? I've already talked about the fact that we should not be thinking about our discipline as a production problem. That's the mistake. If it's not a production problem, then I think it's important we should become world class at learning, because that's what our problem really is. We should be figuring out what the skills are to be able to learn and discover what the right solutions to our problems are. And I think that we should be looking to science to try and apply that kind of thinking to our discipline. And I can't imagine an engineering approach that doesn't embody these 5 principles if we're going to focus on trying to be good at learning. We want to be iterative. We want to employ feedback so we can gather the information from our iterations. We want to make progress incrementally in smaller steps. We want to be experimental. We want to assume that we're going to make mistakes, we're going to try things out, and we're going to measure the results of our experiments. And we're going to be empirical. We're going to gather information from the real world and understand what it means in the context of our software. So let's look at each of those in a little bit more detail. Here's the description of being iterative, again from Wikipedia. Iteration is the act of repeating, oops, sorry, pressed too soon. Iteration is the act of repeating a process, blah, 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 to approaching a desired goal, target, or result. That's the version of this that we're really interested in. We're interested in using iteration to steer towards a useful outcome. Iteration is important because it means that we can learn, react, and adapt to what we learn. Sorry, the layout of this slide got slightly screwed up. So we can do each of those things. We can learn, react, and adapt to what goes on. So it's important in that context. It also allows us to steer towards a goal. It's a fundamental part of the process of continuous improvement. It allows us to refine our practice and improve continuously, and then enhance the quality of our work over time, getting better and better and better all of the time. Without iteration, we don't really get that opportunity. And that also gives us the opportunity to improve our skills and techniques and effectiveness all of the time. We have more opportunities to refine our learning and our understanding and build upon that at each stage until we get better at this. One of the things that I've observed in teams that start applying these kinds of engineering disciplines is that, unlike most software development teams that tend to go slower and slower and slower over time, these teams tend to go faster and faster and faster over time because they become more and more efficient. The next in my list of 5 things is feedback. Feedback is information about actions returned to the source of the actions. Feedback means that we can observe the impact of our choices. We can collect information. We can understand what that means in the context of our learning. I tend to use this model as a schematic for continuous delivery. At the inside of this feedback model is the very, very fast feedback cycle of test-driven development. And at the outside, we're going from idea to useful software in the hands of users. And that's kind of bounds what we're trying to shoot for when we're trying to achieve continuous delivery. So continuous delivery is a feedback-driven model. The next in my list is being incremental. So, and this is a particular version of what incremental means. Evolutionary design, continuous design, evolutive design, or incremental design is directly related to any modular design application in which computers can be freely in which components can be freely substituted if someone improved one or can ensure better performance. So, incrementalism is important. This is about the modularity of our systems. Now, my wife describes me as a serial nerd, but she's mistaken because I'm a parallel nerd, because I can be a nerd on multiple fronts at the same time, which I'm going to demonstrate to you right now. One of my nerdisms is aviation and the space industry. And I want to talk a little bit about something that was influential in my life, is the Apollo space program, as an example of engineering and systems engineering. So here is the Saturn V spacecraft. This is the spaceship that took human beings to walk on the moon, and this was a modular system. So the first obvious module here is this piece. The job of this part of the spacecraft was to get the rest of the spacecraft from Earth into Earth orbit. And then the top part of the spacecraft was divided into a further series of modules. Here are two. This is the command module and the service module. This is the command module, and its job was to essentially, this is where the astronauts lived for most of the journey, but its primary job was to get the astronauts from Earth orbit back down to the surface of the Earth at the end of their adventure. The service module, this part of the craft, was really to get the whole spacecraft from the Earth to the moon and from the moon to the Earth. This is this is the truck that kind of drove everything else on the journey to the moon and back. The next two components are these two. This is the lunar excursion module combined, and this again is divided up into two separate modules. The top part is the lunar ascent module, and its job was to get two astronauts stood up because they couldn't afford the weight of the chairs. They stood up, they went from the moon to lunar orbit to rendezvous with the rest of the spacecraft, and the bottom part of the spacecraft is the lunar descent module, which took everything from the lunar orbit down to the surface of the moon. Now, this is not how the NASA scientists and engineers started off thinking about how to build the spacecraft. Their original vision was more like a kid's cartoon space rocket that took off from the Earth as a whole thing, flew to the moon, landed on the moon, took off from the moon, flew back and landed back on the Earth. It was the modularity of the system that made this trip possible. It meant that they could do it with a much lower energy budget. It was much more efficient to work this way. But also, modularity gave them the option to do all sorts of different things. They could compose the spacecraft in different ways, which they did during different parts of the mission. They could even compose the spacecraft in unexpected, unplanned ways because it was modular. When the Apollo 13 event happened and the service module blew up, one of the pressure tanks, oxygen tanks on the service module exploded and destroyed part of the spacecraft. The astronauts were able to use the lunar module as a lifeboat in essence, and in a way that wasn't originally planned by the mission planners. They flew the whole of that spacecraft back from the moon to the Earth, and without that modularity in the system, they wouldn't have survived. And the last part of this is it allows progress to be made in parallel. So when the Apollo and NASA planners were organizing the work, they farmed it out to different parts of the aerospace industrial complex in the United States. So different firms worked on different parts of the rocket, of the system. So Grumman built this part that's on the screen now, and Boeing built some parts, and Northrop built parts, and so on and so on and so on. So different parts of the American aerospace organizations could work semi-independently of one another and make progress on the mission, on the system as a whole. There's one last important thing that's worth thinking about when we start thinking about incrementalism, and that's this is slightly from a slightly more kind of process technical point of view, and this is the importance of batch size. We can think about making changes. So there are two kind of fundamental approaches to making changes. We can make changes in one large lump and then deploy that into production, which in general, we've kind of tried that lots and it really is a bad idea. Or we can decompose things into smaller pieces, more modular components of the system, and grow the system piece by piece by piece. And that gives us some interesting properties, one of which is a reduction in risk. This is somewhat counterintuitive, but is absolutely borne out in the real world and is measurable. I recommend again to you the Accelerate book if you'd like to dig into some of these ideas in more depth. I'm going to show you some maths. This isn't great maths. It's kind of, forgive my bad language, but it's kind of bullshit maths just to kind of demonstrate the concept. What's the total risk of releasing software? And we can think about that. So for what goes into, there's going to be a certain number of changes, and each change is going to have a level of risk associated. So this is the risk of a given change causing a problem in production when we release it. And so we could think of the total risk of releasing changes into production as the sum of the risks associated with all of the changes. But it doesn't stop there. If we've got multiple changes, then there's an additional risk. There's a risk that two or more of those changes might interact in some unpredictable way. And that's the kind of risk of interaction. And that is really scaled to the power of the number of changes. The more changes we have, the more possibility there is that there's going to be a risk of a defect as a result of two different changes interacting in an unplanned way. So the number of changes is a significant factor in this risk calculation. So we can reduce risk by reducing the number of changes in any given release. So instead of working and creating a large bundle of changes and dumping them all into production, so lots of changes, N is very large, and so the risk is high. So we can manage that risk by having each change is being small, a few small changes, N is small, and so the risk is low. So we can control risk through working more incrementally. Now, I've used two words in the English language that are very, very similar. And whether you're a native speaker or not, these are sometimes confusing ideas. And so I've stolen off a friend of mine this beautiful illustration of the difference. So this is from Jeff Patton's great book on user story mapping. But he has these pictures that describe perfectly the difference between being iterative and being incremental. So if we're going to work iteratively, we work like this. We carry out a rough sketch of what it is that we want, and then over time we modify the sketch and refine it and refine it and refine it until we come to the outcome that we're shooting for. Being incremental is very, very different. Being incremental is about working on little pieces of the whole, and we're going to work on those pieces. Now, it's possible to be both iterative and incremental. We might be iterative in one of the little pieces, but this is the difference between the two ideas. We're going to, so being incremental is about modularity, really. Being iterative is about evolving changes over time. So we need both of those things really to do well. The next in my list of 5 is being experimental. An experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect and demonstrating what outcome occurs when a particular factor is manipulated. Being experimental is really important, and I'm going to go back to the space program again to give a little illustration of that. In 1961, the American president, John F. Kennedy, stood up in Congress and made this very famous speech, which said that they were going to send people to the moon by the end of the decade. And everybody in NASA took a big deep breath and a step back because they had no clue how to do that at the time. When Kennedy stood up in Congress, this was 2 weeks after the first American had a space mission. So the Russians were ahead. Yuri Gagarin was the first human being to go into space. The first American was a man called Alan B. Shepard, and Alan B. Shepard was an enormously brave man who was essentially strapped inside a tin can on top of an intercontinental ballistic missile that was designed to deliver nuclear weapons, and then fired up in a suborbital hop 100 miles up and then parachuted back down in his tin can. Incredibly brave. At the time, these intercontinental ballistic missiles, the Redstone boosters, were blowing up on the pad all of the time. So he was literally risking his life to achieve this. 2 weeks after that, Kennedy's saying we're going to the moon. He's done what leaders do. He's kind of planted a flag on a hill and said, let's try and achieve that flag. Let's try and navigate towards that outcome. You know, I'm a politician. I've got no clue how to do this. You're engineers. You're smart. Figure it out. This is kind of, you know, the way that organizations work. I once had somebody point out to me that this is probably the most expensive user story in all of history, which, you know, I think it's probably in with a shot. Here are some pictures of things that the Americans didn't know how to do at this time. And this is basically all of the things that you need to be able to do to achieve this. They hadn't really got launches sorted at this time. If you look at a montage of the very early 60s of American rocket launches, it's mostly a series of explosions on the pad. They hadn't sorted out the bugs out of the rockets yet. They hadn't got multi-stage vehicles cracked. They hadn't got that. They hadn't got the splashdown phase really mastered. The next mission after Shepard's mission was Gus Grissom, and the capsule sank and Grissom nearly drowned. They hadn't got space suits that would allow astronauts to work in a vacuum. They had pressure suits from high altitude flying, but they hadn't got a space suit that would work. When the first people, both Russian and American, tried to do spacewalks later on, they had big difficulties. The spacesuit being inflated, they couldn't move very well, and you know, they could have died if they hadn't been able to get back into the capsule. So they had to develop that. They hadn't got the mission control stuff sorted out. They hadn't got this modularity idea sorted out. None of this stuff was in place. Nobody had yet docked 2 spacecraft together in space. All of these things they didn't know how to do. And Kennedy just stood up in Congress and said, we're going to go to the moon. So where do you begin when you have a problem at that kind of scale? Well, one of the things that you do is that you hire some really smart people. And this is Margaret Hamilton. This is the woman who led the flight control systems team for the Apollo missions. And she was incredibly smart. She was the first software engineer. She was the first person to think and believe that writing software was a form of engineering, and to try and apply that kind of discipline to writing software. Before that, they didn't think of it in those terms at all. And Margaret started that kind of thinking. So hiring really smart people is absolutely a good starting point. But let's start thinking about the problem. Here's a picture of the Earth-Moon system. And so where do we start on this problem? Except this is not really a picture of the Earth-Moon system. This is a kid's storybook picture of the Earth-Moon system. Here is a more useful picture of the Earth-Moon system to scale. At this point in human history, no human artifact had been more than 1 pixel away from the planet Earth. So problem 1, how do you get anything all the way from the Earth to the moon and back again? That's a terrifically difficult problem. You can imagine the day after Kennedy stood up in Congress and made his speech, the people in NASA getting together and said, what do we do now? How are we going to solve this problem? Oh no, this is terrible. What are we going to do? I know, I've got a good idea. Let's put 3 astronauts into a spaceship, send it to the moon and see if they come back. No, this isn't the job of waterfall engineering. We need to do something smarter than that. I know. We could simplify the problem and maybe keep our jobs if we sent the spaceship to the moon without any astronauts in it and then brought it back again. That is a much better idea. It's probably going to save us having to recruit quite so many astronauts. It's still an enormously difficult problem, though. How do we solve that problem? I know. I've got a great idea. Why don't we just send the spaceship to the moon and land it on the moon without bringing it back? That nearly halves the problem. That is a great idea. That's much simpler. Oh, what does landing on the moon mean? It doesn't have to survive the landing on the moon for us to be able to learn things. And that was the job of this spacecraft. This is the Ranger program. This is literally spaceships as bullets for target practice to see if you can hit the moon. The job of this space program was to shoot these spaceships to see if they could hit the moon. That was it. That was the job. And how did that go? Well, the first mission was planned to just get the spacecraft into Earth orbit, and it failed. Remember what I said earlier? The Americans hadn't got all the bugs out their rockets. This one blew up on the pad. The next one blew up on the pad. If you've ever worked in a big project, the next one might amuse you. So the first 2, their job was to get into Earth orbit. The assumption of the third mission was that they will have proved that and got into Earth orbit by now, and the third mission was to go for the moon. And so they decided to go for the moon anyway. They haven't got things into orbit yet, but they went for it anyway. And they succeeded to the degree in which they got it into Earth orbit, shot off towards the moon, or well, shot off towards somewhere, but they missed the moon entirely. Ranger 4, it worked. It got into Earth orbit, it did the deorbit burn, shot off towards the moon. It hit the moon, but as soon as it left Earth, the spacecraft died. So they lost all information from the spacecraft. They managed to observe it by ground-based observation techniques that they saw it hit the moon, so they knew that they'd had a partial success, but they got no real data. The next one missed the moon again. The 6th one worked. The cameras failed, but they got telemetry, so they got some feedback. They're starting to gather data. Well, they're starting to get more and more data with each one of these missions. The 7th one was a success. The 8th one was a success, and the 9th mission was a success. So you're NASA in the Cold War era. You have essentially an unlimited budget. You have access to the finest minds in the Western world anyway, to try and achieve this. How do you start? You don't start by drawing a big Gantt chart and planning what Joe will be doing in 1969. You start off by figuring out, what do I need to learn, and focusing on that, and then carrying out a bunch of experiments that allow you to learn that thing and to make progress. And then you build on that. The whole of the Apollo program was a vast series of planned experiments. They went from tiny things, measuring the tensile strength of a bolt when it's at cryogenic temperatures, to things like this, using spacecraft as bullets to sit for target practice to see if you can hit the moon. That's how we really learn. That's what engineering really is. This is, when we're engineering in unknown circumstances, this is what you do. So another simple example of being experimental. You may have seen things like this before. The game here is to decide which orange dot is larger. Is the orange dot on the left bigger, on the right bigger, or maybe they're both the same? Make your choice. Decide which you think it is. Here's my experiment. They are, in fact, both the same. Many of you will probably have guessed that. You've seen things like this before. And you know, it's an optical illusion that the one on the right does look bigger, but it's not. Carrying out my experiment allows us to check that that's the truth. Here's another one. Make your guess. Call out which one you think it is. Is the line on the left longer? Is the line on the right longer? Or are they both the same? My guess is that most people watching this talk think that they're both the same, and you're wrong because I cheated. The right line on the right is in fact longer to demonstrate that you can't tell without experimenting. You need to carry out the experiment to know. There's a famous optical illusion where both the lines are the same and they look longer because the arrowheads are in different directions, but that's not this. And you can't tell that without carrying out the experiment. Human beings are kind of programmed to guess about things, and science is about not trusting those guesses. We want to measure things instead. And engineering is, remember, the application of that kind of reasoning to real-world problems. The last of my 5 things, being empirical, based on, concerned with, or verifiable by observation or experience rather than theory or pure logic. I think this is kind of important. We often, I think that software development appeals to the same kind of minds that enjoy things like maths. And I am not denigrating maths in any shape or form, but being empirical matters. It means that we can be evidence-based. It means that we can check our assumptions and our theories. So science is the same. So we can make predictions based on the maths. We can predict that there's going to be a Higgs field and a Higgs boson in the 1960s with the maths, but we don't really believe that's true until we've got experimental empirical evidence to back up those observations. It wasn't until we built a machine that could actually measure the Higgs field that we now change our assumptions about that theory. We can start using evidence. We can start really disambiguating myths from truths, and we can start doing research rather than just working on the basis of guesswork. We can never, ever be certain of success. Progress only comes when we risk failure. We learn most when reality doesn't match our predictions. One of the superpowers of scientific style thinking is that at the point at which your experiment learns is the point at which you really begin learning. If you make a prediction and your experiment just meets that prediction, maybe your experiment wasn't very good. But if you make a prediction and the experiment disagrees with your prediction, then you either know a truth, you falsified your prediction, or it makes you learn how to do better experiments. It forces you down a better road. One way of thinking about this is thinking about automated testing. You put this, into our context. Think about the importance of automated testing. Automated testing is not there to prove that your software is good. We can never have enough tests to do that. But if you have one test that fails, you know that your software is not good enough, and therefore we can reject the change based on test failure. So falsifiability is an important aspect of this kind of thinking. Production is always going to surprise us, and it probably should. We should be taking a risk. Production is a source of the most valuable information about whether our products are the right products and whether they are fulfilling our users' needs and whether they are doing all of the right things. We should be monitoring that information and making decisions on the basis of it. If you think about it, all of our design choices, all of our coding efforts, all of our tests are only ever our best theory to explain things so far. And we should be looking to refine that theory. Again, think of the way that science works. One of my other hobbies is reading about physics. And in physics, the two deepest theories, the deepest ideas, the most proven things in human experience are general relativity and quantum mechanics. These things explain our observations of the universe at the biggest possible scales and at the smallest possible scales with unbelievable levels of precision, and yet they don't agree with one another. You know, at the most extreme points in the universe, places like black holes, and at the start of the universe, they disagree. They don't match. It's not obvious what's going on, and so we know that one of them at least is wrong. And so there are teams all around the world that are funded trying to come up with better theories. We should apply that kind of thinking. We should never think that we are done. We should always be looking to improve and refine our designs and our products and moving them on better, to make them better and better and better all of the time. Continuous delivery, as I said at the outset, I think of as an engineering discipline. It's absolutely grounded in the application of short feedback cycles. Continuous delivery is driven by the idea of working to reduce those feedback cycles. We use test-driven development to evaluate our experiments, tiny mini experiments of what we're doing, high levels of automation to give us repeatability and reliability and to control the variables so that we can carry out these experiments. We use hypothesis-driven approaches to making changes, and we use tests as falsification mechanisms. We use these feedback loops, pervasively throughout the discipline. But really it's about this. And if you've been paying attention, you'll know what this is about. This is a picture of the scientific method. We're going to make an observation of some kind, and we're going to propose a theory on the basis of what we observe. From that theory, we're going to make a prediction, and then we're going to test the prediction in an experiment, and that's going to inform our observations. This is humanity's best problem-solving technique. This, if you have hard problems, this is what you do. This is how you do it. This is how you stop fooling yourself in the way that I assume I fooled some of you with my silly pictures of lines and orange dots. This is how you solve those problems. This is hard work sometimes, but this is what we must do if we want to become experts at learning. We often talk by analogy in our profession. We say that software development, I've heard it compared to making a movie or, you know, bridge building and so on. But I'm not saying let's be like engineers. That's not my advice. My advice is let's be engineers. Let's start applying this kind of thinking to our work. And when we do, I think we'll get a better outcome. That's the end of my presentation. Thank you very much. I'm happy to answer a few questions.
Thank you as well, Dave. Very insightful and as well very motivational, I would say. There are a couple of questions. So the first one is related to, of course, legacy projects. So if you need to introduce continuous delivery in a fairly large existing project,
yep.
Large enough code base, lots of combination of applications and services and so on, what would be the approach, or at least the starting point?
The starting point varies a little bit. So first, forgive me doing some advertising, but I have a YouTube channel and I have several videos on precisely that topic. So if you go to YouTube and search for continuous delivery, you'll see my YouTube channel. And there are several videos on adopting continuous delivery in legacy style organizations. I'm also working on an online training course that covers that sort of stuff. Sorry, that's enough advertising. But I absolutely, it's a more difficult problem when you're talking about doing it in legacy environments. The big problem is usually, there are two significant problems. One of them is technical and one of them is organizational. The technical problem is how do you deploy and test things quickly enough to get feedback efficiently enough to be able to practice continuous delivery. And that's about technically optimizing things and all that kind of stuff. The huge problem that to be honest, that's a significant problem for many organizations, but it's not the most significant problem. The most significant problem is more like, is more organizational. It's because what tends to happen over time is that you build up these big ball of mud organizations that are coupled together. You can't have one part of the organization making a change without affecting another part of the organization. So finding ways to decouple the organizations and decouple the software that they produce is really a significant part of the problem very often. Continuous delivery is, as an idea, is demonstrably more effective than anything else that we know, measurably so. The problem is that it's challenging to adopt, and it's most challenging in pre-existing organizations. However, the very organizations that we point to it as examples of excellence in continuous delivery didn't start out doing continuous delivery. Amazon used to have a fairly traditional development approach with big teams working on a PHP project, and they were developmentally constrained. It was when they divided up into smaller, more independent teams and started adopting the kinds of continuous delivery practices that their organization exploded in terms of productivity and efficiency. So it's possible to make these moves. Ericsson have done some nice writing on applying continuous delivery in the rollout of 5G networks. This is what the biggest, most successful companies in the world do for software development. So it's certainly possible, but it's often a lot of work. And that's kind of what I spend my career these days advising companies on, making this kind of transition. It's not simple. You start by looking at deployment pipelines, start at looking at automated testing, start and looking at infrastructure as code, but also start to look at organizational coupling. How do you make your teams more independent of one another? There are different strategies to achieving this, which I haven't got time to go into now. But take a look at some of my videos. I touch on some of this stuff on some of the.
Definitely check out your YouTube channel and check the videos. And one final question is related to the continuous delivery maturity model. How does it fit into the actually getting back the engineering story?
Mm-hmm.
That was actually so, because there are many companies using precisely your maturity model as a starting point, and of course they adapt it and so on, and it evolves probably.
Yeah.
That a tool which could give us hope that engineering will be back.
I think it is a useful tool, but I think that one of the things that we've learned since the continuous delivery book was released is that there are some better tools than a maturity model to help. So I think maturity model is not a terrible tool, but there's some great stuff in the Accelerate book that I mentioned in my talk about using measures of stability and throughput. The model of the State of DevOps report that they built their stuff around and the Accelerate book is about is kind of based on measures of stability and throughput. So what are those? So stability is a measure of the quality of the software that we produce. You measure that quality by counting bugs. How many defects do I introduce at this point in the process? And how long does it take me to recover from those bugs? So that's the mean time to recover. So those are measures of stability. So the quality of the stuff that we produce. Throughput is a measure of the efficiency with which we can create software at that quality. So you measure throughput by lead time. How long does it take me to go from commit to a releasable outcome? So how long does it take me to traverse my deployment pipeline in continuous delivery terms? And how often, and frequency, how often do I actually put those changes out into production? Now, combined, these things add up to a model that can predict your performance as a team. If you have high scores on on stability and throughput, the Accelerate model predicts things like you'll have higher job satisfaction rates, you'll have many fewer defects in production, your company will make more money, you'll spend 44% more of your time producing new software than teams that have a low score. So this is my tagline for my stuff is better software faster, and this is why, is because there's no trade-off. The data from the State of DevOps report says there's no trade-off between high quality and high throughput. the way that you get high throughput, the way that you get the most efficient route to producing software is by going for a high quality process approach and software. And
understood. Yeah.
That's it.
So Dave, thank you so much for being once again with us. We're definitely looking forward to have you next time. It's been a real pleasure. We're going to have a short break right now. Don't forget to celebrate properly the 10 years.
Will do.
A remarkable moment in time, I would say. So
thank you very much indeed.
Until next time.
Thank you.
We're having a 2-3 minutes break, and then we're going to meet Steven Thayer.